Hello students, in the continuation to the chapter electric charges and fields, here we are with a new topic, that is the points to ponder. We have read about the electrons in this chapter. We have read the protons, the charge they have and the mass associated with them, what kind of electric fields they produce, what is flux, and other various principles and laws like superposition principle, Coulomb's law, Gauss's law, and we have seen various applications with respect to these laws. Now here in points to ponder, we will see few interesting things like reading out the point 1. You might wonder why the protons all carrying the positive charge are compactly residing inside the nucleus. Why do they not fly away? You will learn that there is a kind of fundamental force called the strong forces which hold them together. Range of distance where this force is effective is however very small, 10 to the power minus 14 meter approx. This is precisely the size of the nucleus. Also, the electrons are not allowed to sit on top of the protons, that is inside the nucleus, due to the laws of quantum mechanics. This gives the atom their structure as they exist in nature. See, you have seen one thing in the previous classes, that radius of atom is approximately 10 to the power 10 meter, that is 1 angstrom, whereas the radius of nucleus is 10 to the power 15 or 10 to the power minus 14 meter. That is, our atom is around 10,000 to 100,000 times bigger than the nucleus. And in this small nucleus, we have a range of protons and neutrons lying in it. Protons and neutrons lying in it. Here it is not the radius, it is the size. We compare it with the size, not the radius. So, first thing, in the nucleus we have proton and neutron both in it. Proton carry positive charge, whereas neutrons are neutral in nature. Neutrons are added in the nucleus to provide some mass, and due to the providation of the mass in the nucleus, it makes the nucleus stable. Otherwise, the protons and proton repulsion will be there and nucleus will not be stable. And then electrons tend to move here in the orbits. These electrons are not supposed to be near here, though they face this attractive force. Nucleus attract these electrons. There is always a attractive force existing which gives this proper solid structure to our atoms. And the force which we are talking here is the strong nuclear forces. Strong nuclear forces. These forces are short range forces, and these forces we will be able to find inside an atom only, and they determine all the phenomena happening inside the atom. These strong nuclear forces are responsible for all the interaction which happens in the nucleus and around the nucleus of an atom. Now the second one, Coulomb force and gravitational force follow the same inverse square law, but gravitation force has only one sign, always attractive, while Coulomb's force can be of both signs. It can be repulsive if we are having the same charges. It can be attractive if we are having the polarity of difference. Allowing possibility of cancellation of electric forces. At a point, electric forces can zero, but gravitational force will always have some or the other magnitude. This is how gravity, despite being a much weaker force, can be a dominating and more pervasive force in the nature. This is one of the reason why it is this our gravitational force is dominating and pervasive. Why? Because it is always positive and at every point it do exist, whereas like electrostatic force is positive and negative and at a point can cancel out and become zero also. Third, constant of proportionality K in the Coulomb's law is matter of choice if the unit of charge is to be defined using Coulomb's law. In SI unit, however, what is defined is the unit of current A via these magnetic effects Ampere law, and the unit of charge Coulomb is simply defined by IC equals to 1C equals to 1 AS, that is 1 coulomb equals to 1 ampere second. A charge is current into time. From this we can derive this formula. This is also a very important formula, one should remember it. Then in this case the value of K is no longer arbitrary. It is approximately 9 cross 10 to the power 9 Newton meter square per coulomb square. That is when we are defining a coulomb or the charges present in a system. In that case our value, the constant proportionality, is not a arbitrary value. Then we have approximated it to 9 cross 9 into 10 to the power 9 Newton per meter square per coulomb square. Now fourth point, whether the rather large values of K, that is large size of the unit of charge, from the point of view of electric effect arises because the unit of charge is defined in terms of magnetic forces on current carrying wire, which are generally much weaker than the electric forces. Thus, while 1 ampere is a unit of reasonable size, the magnetic effects, that is 1 coulomb equals to 1 ampere second, is too big a unit for electric effect. Here what they aim at stating is this: the value of K is defined in accordance with the value of charge, the coulomb we have taken, and if we are defining the K and the value if for 1 coulomb is coming around 1 ampere per second, this is all due to the moving charges. Ampere is current due to moving charges. Only this ampere is produced only by moving charges, current. So it depends upon the magnetic force also. It depends upon the magnetic force. In a system, if E and B, electric field and magnetic field, are working, then only it will produce current. So when we are talking about the current, it is very much important for us to include the magnetic forces also, and these magnetic forces are much weaker than the electrostatic forces. That's why this 1 coulomb of unit is a very big unit for explaining the electrical effects in a system. The additive property of charge is not an obvious property. It is related to the fact that electric charges has no direction associated with it. Charges are scalar. Because charges are scalar, they are added like the normal numbers. Because charges are scalar, they are added like normal numbers. Charge is not only a scalar or invariant under the rotation, it is also invariant for frames of references in relative motion. This is not always true for every scalar. For example, kinetic energy is a scalar under rotation, but is not invariant for frames of references in relative motion. Like whenever we are considering a relative motion, we can provide a particular direction to the kinetic energy also. But when we are comparing a charge in the same frame of reference, we can give a position to the charge, but we cannot decide in which direction it is giving us the electric fields, but it is a arbitrary one, and it have in all the direction it have its electric field. They are radially distributed, no specific direction. Conservation of total charge of an isolated system is a property independent of scalar nature of the charge. Conservation refers to invariance in time in a given frame of reference. A quantity may be scalar but not conserved, like kinetic energy in an inelastic collision. Kinetic energy is always like it is conserved, but these scalar quantities may not be conserved. On the other hand, one can have conserved vector quantity, for example, angular moment of an isolated system. What they aim at saying here is that we have seen in the kinetic energy and potential energy graph that if potential energy is maximum here, when the body goes down, it will attain the kinetic energy. So these are changed, these energies are being conserved. But when we are under a system and tend to explain a charge q, this charge q may not be conserved because it is a scalar. We cannot define its property of conservation. So this charge in the system cannot be conserved, but if it is a proper system with few vector quantities, like we are explaining electric field or the force, these are vectors. So if we are defining these two things from here, we can say that the charge is being conserved in this system. Maybe it disappear and it can give its whole of things to the other charge or any other part of the system, but this is conserved. But mostly the scalar quantities, they do not follow up the law of conservation. Quantization of electric field is basic, unexplained law of nature. Interestingly, there is no analogous law on the quantization of mass. Like quantization of mass is a simple and a straightforward hypothetical given equation which satisfies the mass addition at every point. In the similar way, electric charges are being quantization, but in nature it is unexplained because masses are big enough to be calculated and charges are small. So it is little tough for us to do the calculation with the help of charges. Now, superposition principle should not be regarded as obvious or equated with the laws of addition of vector. Like superposition principle is a quite additive principle. We are adding so many field lines and forces, like F net equals to F1 plus F2 till so on till Fn. So we are doing addition, but this is not a synonymous thing to the addition of vectors. Addition of vectors follow a different pathway of addition. It says two things: forces on one charge due to another charge is unaffected by the presence of the other charges, and there are no additional 3 body, 4 body, etc. Forces which arise only when there are more than 2 charges. So see, in this we have seen like F1 is defined for Q1, Q2, F2 is defined for Q1, Q3 and so on. We do not determine a situation where there is a force on the charge Q due to charge 3 and this force is having a resultant force on charge Q1. There is no such chain charge procedure is happening. Okay, so that's why we can say that superposition principle should not be regarded obvious and it is not as equivalent to addition of vectors. 10th, electric field due to the discrete charges. Sorry for the disturbance. The electric field due to the discrete charge configuration is not defined at the locations of discrete charges. For continuous volume charge distribution, it is defined at any point in the distribution. For a surface charge distribution, electric field is discontinuous across the surface. Like if you see a surface, particularly a surface which is not spherical, we have taken some rectangular surface. In this, if we calculate electric field from here and from here, they will have some discontinuity. It will direct over here and it will direct over in like to your face. This is a three-dimensional view. It will direct to your face coming out of the plane of the paper. So this is over this particular point they are showing the discontinuity. 11th, electric field due to a charge configuration with total charge 0 is not 0, but for distance large compared to the size of the configuration, its field falls off faster than 1 by r square, typical of field due to single charge. An electric dipole is the simplest example of this fact. Here it is saying that like this is our electric field and we have charges placed very far. So in between here there will be electric field lines, but if we see we will not find any charge over here, but we will see that charge over this point is 0, but there do exist electric field. You are sitting at a place, you cannot see the electric field, you cannot see the charge, but there is electric field all around you. All over the surface of the earth we have electric and magnetic fields which actually helps us during our many natural phenomena, like the cosmic rays which are entering in our surrounding are deflected by these earth's electric and magnetic fields. Then the waves formation in the ocean do have some component with respect to these. The Wi-Fi's we are using, they are also affected by these E and B, and many other electrical phenomena which are happening all are affected by E and B. And biggest of that example is the cosmic ray retraction due to the presence of electric and magnetic field on the surface of earth, which is actually our savior. Like the ozone in the stratosphere helps us protecting us from the UV. These cosmic rays which are high energy electromagnetic waves, if penetrated through our body, can create a lots of diseases, and most promptly is the genetic disease as well as the mutation and the cancers. They are being reduced by the natural electromagnetic and electromagnetic field lines present on the surface of our earth. So there do exist field line everywhere, and one of the simplest example they state is a dipoles example. Dipoles example, as this dipole is a small body having a positive charge on one side and having a negative charge on other side, and dipole moment works in from the negative to the positive side. And if we consider a point somewhere here on the upper slide, see on the top of the slide point here, it is too big when compared to the size of our dipole. Point P's position is much larger than the R. We'll take R or 2A. So at this point there will be electric field at point P due to these two, but they will fall like electric field will fall as 1 by R cube. So very extremely small electric field will be there affecting the point P. Extremely small E. will be at point P. Extremely, because it deals in this manner, E proportional to 1 by R cube. So these are the few points which are extra than the chapter, which are for you to imagine, for you to understand the concept. We have taken many things in our chapter, we have assumed at one or two places. The assumption is very much necessary, because every time we cannot provide a certain things when we are dealing with a microscopic world. So these are the few concepts which need to be explained. So we are done with the chapter number 1. So now I'll give you some tips and tricks for reading physics. So make a habit of reading textbook of physics, which I think many people don't do. Most of the people, what they do, they will solve a lot of questions and will not go through the content of a chapter. So once if you are not going to the content of the chapter, you are not thorough with the reasons provided in the chapter for taking that particular equation. Now when we were dealing with the dipole, we have seen in the denominator we have r square by a square to the power 1 to the power 2 or 1 by 2 or 3 by 2. Okay, we have these many powers. So at a point we have put this a as negligible, and you are reading a formula where denominator is r cube. You have by hearted this formula, but you don't know from where this formula came. So in case if they are giving you this formula and saying that the dipole is not smaller, dipole and the distance to the point P is equivalent, at that point also you will use this formula and you will get a wrong answer. So it is very much important for a student to read the chapter of the physics given in your books. Read it thoroughly and read the way you read biology. So mostly it is said that a chapter should be read 2 to 3 times, and make the same habit with respect to physics also. Read the chapter at least 2 times and make a formula chart. Then derive the formulas instead of by hearting them. Formula chart is for your quick revision, but when you are reading the chapter for 2 to 3 times, at that time take a separate paper and derive a formula. Derive all these formulas, how it is coming, like we are seeing F equals to ma. How that is coming, we need to find out, like a body having some weight and then we are introducing it in the gravity and we are finding this acceleration. For F we can write mg also. Why this why over here it is g and why over here it is a. So this should be understood once you start deriving the formula. And why I am asking you to take a separate paper, because in a separate paper if you are writing, you can file this separate paper in a separate file, and once when you are done with reading your chapters, you can just go through these separate papers and revise how did you did the derivation, or you take a separate notebook for all the derivation. Understand the diagram before mugging up the concept. If you are just going through the concept, first go and check the diagram, how the diagram is, where are the arrows pointing in the diagram, what is the positive q position, what is the negative q, or if you are going to the kinetics, if you are reading kinetics, where is the position now, where was the final position, initial position, and all you have to see. The diagrammatic representation is the easiest representation. So once you understood the diagram, it will be very much easy for one to understand the concept. Try to explain through the diagrams to yourself. Like, you are a student, you cannot explain it to anyone, you can take a class seminar or something, but for you, your own self, you need to explain it to yourself. So just explain yourself what the diagram is trying to convey, and try to derive some kind of equation or formula using that diagram. So you will have a proper understanding. Like, diagrams will tell you why at a point we have taken a positive charge and why at a point we have taken a negative charge. Always write formulas with SI unit. This is very much important. Whenever you are writing this formula, as I am writing force, I should write it in the bracket Newton. mass is kgs, and our A is meter per second square. So this should always be practiced. If you are not practicing this way, at least practice like this, equals to MA, that is kg meter per second square. So that one thing, we will be able to equate these SI units. Secondly, this should not be done in the fair notebook or during your examination, but when you are practicing in your daily routine, so that you will, one thing you will learn the SI units, you will learn SI units, you will learn the relation of various SI units. So again and again, if you are writing, repeating the writing pattern, you will be able to remember all these units. And once you remember the units, sometimes it makes easy for us to solve a question, sometimes it makes easy for us to derive a question. Solve as many as question possible for the clarity of question concept. For each and every concept, like I have taken so many lectures, in that just pick up first one, that is introduction. Introduction to ECF. So in this introduction, solve around 10 to 15 questions. Simply in this introduction itself, you will find more than 50 questions in your in this references book, and on the websites, on the internet, you will find so many questions. So just I'm just telling you the minimum amount of question you can solve from this simple topic is 10 to 15. Once you solve 10 to 15 question, you will get a clarity, like you will get clarity on your own understanding. How much did you understand the introduction, and how did you understand that? Did you understand which kind of material is taken negative, which kind of material is taken positive, and why they are taken positive and negative? Okay, then refers notes provided in my class. So the notes is handwritten, and they are wrote very much properly, and they contain all the important points in it, all the important points. So make a note while you are reading, going through these videos. Make a proper note, get a separate notebook, make the notes, use color pens if needed for your own understanding, and keep this notebook separate. So once you are making these particular notes, at the end, and when you are going for the revision, go through these notes. As they are colorful, they will not be boring, and these all notes are very much self-explanatory, and it will help you to learn the subject. Relax is the most logical subject and most easy to learn. Physics is one of the logical subject. It have logics everywhere. We do not need to there are no such exceptions which we see in chemistry, and it goes in a flow. Everything you can correlate in your day-to-day life. Electricity is such an important part of your life. The motion you see, the top you play with, and the marbles you play with, the force we apply, the doors we pull and push, and the ray optics and wave optics, if we see the eyes, binoculars, microscope we have seen, telescope we have seen, and in our day to life we are using mobile phones, which are an example of electromagnetic waves, radio waves. Then we are treating the patients with radiations, that is another example of electromagnetic waves, like gamma rays, x-rays. Diagnosis, we are using all these things. So see, whatever chapter, whatever concept you are going to read in physics will be used in your day-to life. At every step it have its own use. So it is the most logical subject and most easy to learn also. You do not need to by heart any concept in physics. Everything, if you understand in a practical way, there is no need to by heart. You will understand it very simply. So take it as a plus point that you are a physics student and you got fortunate enough to learn the physics. Once you will start following up these tips and tricks, by the end I can say that you will be the best in physics. So try these tips and tricks, and we'll meet in the next class with a new chapter. That's all for today's class. See you soon. Bye bye.